Thank you very much. My name is Gorghetto. I'm a postdoc at Weizmann, and today I will tell you about a work I've done in collaboration with Ed Hardy and Nicolaescu, where we pointed out a new signature of invisible axions. And by invisible here, I mean axions that don't necessarily couple with the standard model, and therefore that are not even in principle detectable with the conventional experiments that are based on the standard model couplings and on the local matter abundance. And indeed, these couplings are not even guaranteed to be there except for the use of the axion. So the key point is that axions, thanks to their some nature, can form cosmic strings in the universe. And during the evolution of the universe, the strings emit gravitational waves, which can be detected in multiple experiments. So in this talk, I will make the minimal assumption that our theory has one axion, which is defined to be the Goldstone boson of a continuously broken global U1 symmetry, also known as Peccei-Quinn symmetry. And the symmetry is also explicitly broken by the axion potential V, which is a periodic function of p 2 pi Fa, and leads to the axion mass Ma. So I will keep the relation between Ma and Fa free, but for the UCD axion, as you know, is fixed by UCD, particularly Ma times Fa is also more as n pi f pi. And Ma and Fa will be the only three parameters in the following. So the simplest implementation of this spontaneous breaking is assuming that the axion is a phase of a complex scalar field phi, also known as Peccei-Quinn field, with mass-scalar potential. And this actually happens in many UV models for the QCD axion. And I will call MR the mass of the corresponding heavier-than mode of this Peccei-Quinn field. And this MR is also of the order of Fa if the mass-scalar potential has order 1 quartic coupling. So a crucial observation in the following is that the initial conditions for the axion field are inhomogeneous, especially inhomogeneous in the universe, if the universe temperature was larger than Fa, or if the apogee inflation was larger than Fa. So in the first case, the inhomogeneities, the inhomogeneities are produced by thermal fluctuations. In the second case, they are produced by quantum fluctuations during inflation. So if the initial conditions are homogeneous, like in these cases, besides axion waves, the equation of motion of the complex scalar field phi admit other solutions, which are called axion strings, and will be generically present in this scenario just by randomness. And the strings are essentially one-dimensional objects where the phase of phi, which is the axion, wraps non-trivially the fundamental domain minus pi and pi once as you go around a circle in space. So one of the most important properties of the strings is their core. So they have a core with size 1 over mr, which is also of the order of 1 over Fa, the Peccei-Quinn symmetry breaking scale for the 1 quartic coupling. So strings store quite some energy in them, and this energy is usually expressed in terms of a so-called string tension mu, which is defined to be the energy of the string's per unit length. And is given by two contributions, one coming from the core, pi Fa squared, and another coming from the axion gradient. And this corresponds to a logarithmic divergence factor, which is cut off at a typical distance between two strings with opposite orientation, which in the early universe is the inverse sample. So the string tension is pi Fa squared times the log of mr over h. In particular, it occurs logarithmically since h decreases in time. So although strings are stable when not taken alone, when taken together, strings can interact between each other, emitting the energy they store into axion waves. And it has been shown that in an expanding universe, after a string system is formed, thanks to this interaction, the string system evolves towards a cosmological attractor, also known as scaling regime, which is defined to be a regime where the number of strings per volume is approximately constant in time, is preserved in time. And this regime is also reached independently of the string density in the initial conditions. So it will be asymptotically reached in the universe, and therefore it's called a attractor solution. So in this solution, in order to maintain a fixed number of strings per volume, the string system needs to lose energy. And this is done by emitting axion radiation or just axion waves with a rate given just by Nernst conservation by psi mu over the cube, where mu is the string tension we defined before, psi is the number of strings to double patch, and there is a dimensional parameter with that count the number of strings to double volume, or if you want, the average string length, one Hubble volume, units of the Hubble radius, average all the Hubble volumes in the universe. And in particular, it has been shown recently that psi is not exactly constant during the scaling regime, but as logarithmic relation. And in this plot, indeed, they show the evolution of psi as a function of time, which is represented by log, for different initial conditions. And as you see, during the scaling regime, which is the one in black, psi grows logarithmically in time, particularly psi proportional to log of a MR of h. This plot also shows that the scaling regime is an attractor in the sense that all the initial conditions tend asymptotically to this scaling solution. So this corresponds to logarithmic violations in the sense psi grows with log instead of being exactly constant. So this also means that the energy emitted into axions, in order to maintain the scaling regime, is proportional to RH over the cube, where the two logs come respectively from psi and mu, and the Fa square comes from mu. Okay, in this video, as an example, I show the numerical evolution of the string system, and the cube here represents the Hubble horizon that increases in time. And although the total string length diminishes, the length of the strings inside the Hubble volume remains approximately constant in time, up to dimension scaling violations, and this is the result of the existence of the scaling regime. So the scaling regime ends when the Hubble parameter is equal to the axion mass, at which time the string system gets completely destroyed after the formation of a network of domain walls. And at this time, the log of MR H, which you can think of log of Fa of H, which I just call log in the following, is about 70 for the UCD axion and 100 for ultralight axions. So after the system gets destroyed, no strings in domain walls are anymore present, and only axions are present, and they form a component of the dot map that we observe nowadays. So crucially, during the scaling regime, the motion and direction of the strings, besides sourcing these axions, they also source gravitational waves, which are the main focus of our work. And the ingredients which are needed to calculate the gravitational wave spectrum are essentially two. So first, we need to understand what is the energy emission rate in gravitational waves, gamma g, which is the energy density emitted per unit time in gravitational waves by the string system. And then we need to understand what is its momentum distribution, which I call d gamma g in decay. And then the total spectrum, total gravitational wave spectrum from the whole scaling regime will be given by the integral over time of d gamma g in decay. So unfortunately, unlike axion waves, whose energy is fixed by energy conservation and therefore only essentially by psi, this energy gamma g cannot be only argued by energy conservation. However, we've been able to relate it to the energy emitted into axion gamma a via the low energy effective field of the strings, which is the number Walter effective field coupled to the axion radiation by the Cardamom term, modulo an order 1 coefficient, which we then extracted by the numerical evolution of the field equations. So in particular, the string effective field describes the evolution of the string, which is represented by the collective coordinates mu, and radiation, which is just the axion field A. And this effective field predicts that the ratio between the energy emitting gravitational waves and the in axion is given by g mu square over a square times a dimensional coefficient r. And this coefficient is a function of the string trajectory, but can be shown to be invariant under the scaling of this trajectory. In particular, depends on the shape of the strings, since it's invariant under the scaling. So since the average shape of the strings is preserved during the scaling regime, we expect this relation to hold during the scaling regime, hold to the tractor solution, with coefficient r to be constant in time, only because the average string shape is preserved. So therefore, multiplying this relation by gamma a, we conclude that gamma g is given by gamma a times g mu square over a times a dimensional coefficient r, which we assume to be over the 1. So in particular, gamma A is completely fixed by energy conservation by psi mu over the cube, and therefore goes, as I said before, like log square over the cube, while mu goes like log, and therefore gamma G is proportional to log to the fourth over the cube. In particular, this proportional factor of mu square comes from the fact that the cross source of gravitational waves is the energy momentum tensor, which is proportional to the string tension itself. So we then actually numerically simulated the system during the scaling regime, and besides confirming this relation, we've been also able to extract numerically this order 1 coefficient R, which is indeed over the 1, is about 0.26, and it is constant in time. And this corresponds to a wonderful confirmation of the analysis of the numerical effective theory. Also, we have been able to extract in these numerical simulations the momentum distribution of this energy density, which I call the gamma G in decay. And this momentum distribution is picked at every time at momenta over the Q Hubble, let's say, with a decrease proportional to k minus 2 at higher momentum. And this holds at every time. So, as I mentioned initially, the total gravitational wave spectrum from the whole scaling regime is given by the time integral of this instantaneous limit spectra, the gamma G in decay. And after performing this integral, the total spectrum is approximately scale invariant, in the sense that the G into k is approximately constant. However, since the lower momenta of the integrated spectrum are emitted at later times, thanks to the log to the fourth increase of gamma G, they're also emitted a factor of log to the fourth more efficiently. And this in the end leads to a log to the fourth of k violation of scale invariance. And being the relevant value of log about 100, this greatly enhances the amplitude of the spectrum at low frequencies. So essentially, the violation of gamma G, which comes from the trinomial of mu and of psi, implies that the lower momenta, which are emitted at later times, have a larger amplitude proportional to log to the fourth, and this leads to a larger spectrum at low frequencies. So in this plot, I finally show this gravitational wave spectrum for different choices of the atmospheric constant Fa, is more than 10^15 GeV, and for different choices of the axion mass Ma, is more than minus 18 eV, which, as we'll see next, are not ruled out by dot matter and dark radiation overproduction. So Fa determines actually only the amplitude of the spectrum, which goes like Fa to the fourth, while Ma instead determines only when the domain walls form and the network decays, so when the scaling regime ends, and therefore they determines where the IR cutoff spectrum sits. For smaller masses, the scaling regime ends at later times and corresponding to smaller frequencies of this IR cutoff. So this log to the fourth deviation of scaling invariant I mentioned before are evident, and thanks to the approximate scaling invariance, the spectrum is actually observable in multiple experiments. In particular, thanks to this enhancement at momenta, pulse of timing arrays will detect the spectrum if Fa is larger than about 10 to the 14 GeV, and LISA will detect it if the spectrum is larger than about 5 to the 14 GeV. And a possible explanation of this NANOgrav result would require Fa larger than 10 to the 15 GeV, which, as we'll see next, is in tension with dark radiation bounds. So these results, of course, apply to any axion, in particular to the QCD axion. However, for the QCD axion, Fa in this scenario is bound to be more than 10 to the 10 GeV because of dark matter overproduction. And for the QCD axion, unfortunately, the spectrum is not detectable. So in this upper axis, I also show the temperature of the universe when most of the gravitational waves with frequency f are emitted, and also I show the log at these times. So the spectrum gets deformed, in particular at momenta, which correspond to the temperatures when most of the graphene decouple, and the largest deviation happens at the graphene phase transition when most of the graphene decouple. And the spectrum at higher frequency is more suppressed because higher frequencies correspond to larger temperatures, and at larger temperatures, more are coupled to a standard model, and the universe expands faster. So I just want to point out that a precise measurement of the spectrum could hold information about the presence of additional degrees of freedom beyond the standard model in equilibrium with the thermal path, because this would change the shape of the spectrum. So given the minimality of this theory, which is just one axiom, the fact that the spectrum is observable in multiple experiments is a very strong beyond standard model motivation for the construction of these experiments. So finally, I show the constraints we derived on the axion mass and the constant in this post-inflationary scenario. So first, most of the axions which are emitted during the scaling regime become non-relativistic soon after the time at which the Hubble parameter is equal to the mass, and therefore they form a component of the dark matter. And we computed the dark matter abundance from strings for ultralight axions. And it turns out that the dark matter abundance has exactly the same parametric dependence as the free inflationary misalignment, but is an answer of a factor of about 10 to the fourth due to the increase of the string tension and on psi. And the corresponding bound is shown here and tends to exclude the large values of Fa and large values of the axion mass. Also, the string network decays after BBN for ultralight axions, and therefore the axions that are emitted during the scaling regime act like dark radiation during BBN, and then down from that an effective at BBN tends to exclude this axion in particular tends to exclude larger decay constant larger than 10 to the 15 GeV. Also, dark matter axions have isocurvature perturbations, which are constrained by Lyman alpha observation and C of D observations. And in the end, if MA is small enough, in particular 10 to the minus 28 eV, the string system persists even at the time of decoupling, at the CMP decoupling, and the string system is constrained by CMB observation. Particularly, if FA is too large, the strings would distort the CMB anisotropies, and this leads to a bound on the absolute constant for masses more than 10 to the minus 20. So as a result, despite these bounds, there is still about 1 order of magnitude of allowed values of FA and a lot of order of magnitude of allowed value in MA, for which gravitational waves from strings are detectable. And in particular, the non-detection of these gravitational waves would exclude all the values of the constant which are larger than this SKA observable line. So in particular, these constraints do not depend on the possible axion coupling with the standard model, which we did not specify. And so these results and these bounds would apply to a wide variety of models, most of which are not actually under detection or under observation today, because these models will actually only be sensitive to the gravitational coupling of the axion and not to the standard model couplings. Okay, so concluding, the string scaling regime producing a Dawson-like scaling invariant spectrum of gravitational waves, but the fact that, in particular, the fact that the gamma is proportional to log to the fourth, which comes from the increase of the string tension and mu, leads to logarithmic violation of scaling invariance. This log, being 100, enhances a lot the spectrum at low frequencies. And the spectrum is therefore visible in multiple experiments for FA larger than 10 to the 14 GeV, with the best prospects being in pulsar arrays and LISA. Also, the post-inflationary scenario is bounded by that matter dark radiation and isocurvature perturbations. However, still FA larger than 10 to the 15 GeV and MA between 10 to the minus 28 and 10 to the minus 18 eV is viable and produces observable gravitational waves. And in the future, it would be nice to apply the same first principle calculations to understand where the sum of these effects, in particular the increase of psi, is present also on local strings. Okay, thank you very much for listening.